Hello. One of the most important recent developments in the EDA standards domain has been the actual E164 EDA Common Metadata Standard. For those of you that have been in this industry a long time and remember the days before the generic equipment model, or so-called GEM, this is back in the late 80s, early 90s, we had a situation where every major chip maker had their own version of SEX2 implementations. And in fact, Hitachi had the one, TI had one, IBM had one, Intel had one. Everybody's implementation was different. What that meant for the tool suppliers was they had to have a different version of their communications interface for each major customer. That was a mess. And so the major end users got together in the early 90s and said, let's define the way that we all want to use the SEX2 standards together. And they defined GEM as the way to do that. The same situation occurred in the early implementations of EDA because even though the communication technologies were very standardized and regular, the actual content of the model, which is what really makes the big difference, was very different. There were no explicit guidelines for what should be in an equipment model and therefore what was going to be represented in the interface. And so luckily we recognized that early on, and the standards community got together and defined the EDA common metadata that'll specify what's required in the equipment models. So this was a very, very important evolution of the standard, and it's now being required by a number of major chip makers. So today we'll talk a little bit about what's in that standard and why it's so important. So first of all, what does E164 specify? Well, it is a complementary standard to the E120 and E125 node and self-description standards that states the requirements for state machines, substrate locations, event naming, some of the hierarchy and the requirements for what has to be represented. So it makes sure that the common elements of all equipment are in fact represented in the model in an identical way. Now, this actually enables the users of those standards on the sort of host and application side to make pretty big assumptions, important assumptions about the naming of events and parameters and modules, and therefore be able to create generic data collection plans and even entire applications that leverage that knowledge to keep from having to build equipment specific applications. So again, this is very important. But it's a lot more fun to see the thing in actual working. So another feature of E164, of course, since it's targeted for 300 millimeter wafer fab equipment, one of the requirements is that all of the GEM 300 standards have to be fully implemented in E164. It also requires that the more recent module process tracking standard, the E157, be implemented. And so you'll see that as we browse one of the models. So let's look at this picture now, just as an example. The modules that are the messages that deal with substrate tracking. If you remember the E90 substrate tracking standard, there are two principal objects represented there. One is the substrate itself, and the other is a substrate location, which is a place in the equipment that a substrate can land. Each of those objects has multiple state machines associated with it. The substrate object itself has a transport state machine and a processing state machine. The substrate location has a single state machine which defines its status. Is it occupied or unoccupied? And if it's occupied, what substrate is there? So we'll be actually looking now into the same model that we have in our simulator to see what that looks like. So let's bring up our application here, and you can see that we have the 300 millimeter equipment model here. Let's go find where the substrate location is in the processing chamber. And you can see down here is a state machine for an E90 substrate location, and you can see that's under the actual material location for processing substrate. If you expand that state machine, you will see that there are the same four states that are defined in the semi-standard. The two principal, four transition events. The two principal transition events are unoccupied to occupied, and the reverse, occupied to unoccupied. So those events fire every time a wafer arrives or departs a particular location. Now, if you expand each of those events, you can see that the parameters that are required to be available at that event are the location ID for the substrate location you're looking at, and the substrate ID that has moved in or out of that location. And so what this allows you to do actually is to automatically create data collection plans if you want to track wafer movement within a piece of equipment. Let's go look at a data collection plan that was automatically generated for that. Let's look at the Processing Chamber 1 substrate location plan. You can see that one here. It has two events that are defined. One is the unoccupied to occupied event and the occupied to unoccupied. If we trigger on those event reports, we can see what information we want to provide when those events fire. Again, as we edit one of those requests, it actually pulls up the model. We can see the event that we highlighted here, and we can see that the data we wanted is the substrate location ID. But again, it's more instructive to see actually running. So let's look at, we notice the one is already active. So let's look at the data reports. And let's go find the substrate. Here we go. Here we are. Processing Chamber 1 substrate location plan. We can see here that the event from unoccupied to occupied has fired, and we can see that the substrate ID that went to that location was from carrier 1, and it was substrate number 25. And so every time a wafer moves, you can see it flow through the system. Now, the other important part about E164, though, is that it requires that you have a module for each of the important processing locations. And given that these modules are required, you can actually generate a graphical user interface that matches those elements. So this GUI screen here was actually generated programmatically from the content of the model with no custom code whatsoever. You can see here that it's frozen because we have stopped the data collection reports. But if we go and reactivate those reports, you can see that the animation of that user interface is happening as the events that were defined in those data collection plans fire, and the data from those is collected and used to animate this screen. So the benefit of E164 is that not only do you have standards for the model content, you can actually programmatically generate representations of the tool, data collection plans to collect that data, and actually animate these representations with no custom software whatsoever. So you can imagine the kind of applications you could build with that kind of information beyond just the basic visualization. So, and we'll have lots more to say about E164 in the future, but hope this has been instructive. Thank you.